Welcome everyone. I am excited to present on the topic of architecting security-first enterprise systems. Today, this session will cover how to build security into your systems from ground up and scale it across your organization through DevSecOps practices. In today's agenda, I am going to cover why security first now, and security first lifecycle and use case snapshots and metrics that really matters. So why security first matters for enterprise system? Security is no longer an optional add-on for the enterprises. It's a critical requirement to protect against growing threats and safeguard sensitive data and systems. The security landscape is constantly evolving with the new vulnerabilities, attack vectors, and sophisticated hacking techniques emerging all the time. Enterprises must stay vigilant and proactive to keep up. Robust security is now a core business imperative. Breaches can result in significant financial losses, reputational damage, regulatory penalties, and operational disruptions. Enterprises that prioritize security first are better positioned to maintain trust, continuity, and competitiveness. So move to next slide. Security is foundational component that must be embedded throughout system design, build, and operation to counter sophisticated cyber threats in today's digital landscape. Cybercrime costs are projected to reach 10.5 trillion annually by 2025, underscoring the needs for robust defenses. Like Scott in the keynotes, he mentioned this piece. So expanded attack surfaces from cloud, IoT, and AI tools require proactive integrated security approaches. Attackers constantly evolve tactics with advanced persistent threats, ransomware, and supply chain attacks, demanding vigilance. Embracing security first principle from the start builds resilience and safeguard assets, reducing remediation cost. Proactive threat modeling identifies vulnerabilities early to minimize attack surfaces and enhance inherent security. Adhering to principles of least privilege limits the impact and compromised accounts. Using secure defaults and automating compliance checks ensures continuous security. Move to another slide. So the business imperative. Cybersecurity is a critical business imperative that impacts financial health, reputation, and long-term viabilities. The proactive security first approach can transform potential liabilities into strategic advantages, offering a significant competitive edge. Robust security prevents financial losses from breaches and ransomware, minimizes cost system downtime, and helps avoid regulatory fines. Preventing data breach is crucial for maintaining customer trust, brand loyalty, and attracting investors. The proactive security measures are essential for meeting global data protection regulations and reducing legal exposure. Strong security differentiates companies, attracting disconcerting customers and partners, and enable faster, more secure innovations. So in this slide, I am going to talk about reactive security versus integrated security. The traditional security approaches often fall short in addressing modern threats. Reactive security is an afterthought applied late in the development cycle as a response to detected vulnerabilities or breaches. Reactive security is more costly and complex to remediate as issues are discovered closer to deployment or in production. Reactive security focuses on fixing known weaknesses, leaving systems open to zero-day exploits and novel attack vectors. Reactive security is primarily driven by compliance requirements rather than inherent risk mitigations. Come to integrated security. Integrated security, on the other hand, embeds security into every stage of the system lifecycle, from conception to operation. Integrated security is most cost efficient as it proactively identifies and mitigates risk, leading to significantly lower remediation cost. Integration security creates a more holistic and resilient system by anticipating threats and building defenses from the ground up. The integrated security is driven by a comprehensive understanding of risk, leading to more robust and adaptable security postures. So next slide, security by design, a proactive life cycle. Security must be considered from the very beginning of the system design process, not just bolted on later. Integrating security rather than reacting to vulnerabilities is crucial for building resilient enterprise systems. The security by design lifecycle shows how security is continuously embedded throughout the entire system lifecycle, from initial definition to design, development, deployment, and ongoing monitoring. Defining security requirements upfront, designing with security in mind, developing securely, deploying with the security controls, and continuously monitoring for threats. This approach significantly reduces cost, minimizes risks, and builds inherent trust in your application and infrastructure. Secure design. Secure design is the first stage in the life cycle. So, secure design is a fundamental phase of a security first approach where security is embedded into very blueprint of enterprise systems. This proactive strategy ensures potential vulnerabilities are addressed before any code is written, drastically reducing future cost and risks. Key elements of secure design includes threat modeling and analysis to identify and analyze potential threats, vulnerabilities, and attack vectors early in the design phase. Security architecture reviews to scrutinize the system architecture for security flaws and ensure security principles are integrated into core design, defining clear, measurable security requirements and controls that guide the entire development lifecycle. Applying established secure design patterns and principles to mitigate common vulnerabilities and ensure the system is inherently secure against known and emerging threats. So, I am talking just threat modeling workflow. The goal of threat modeling is to proactively identify and mitigate potential threats to a system. This workflow outlines the key steps in threat modeling process. First, we need to define the scope and identify the most valuable assets that need to be protected. Next, we will identify potential threats and attack vectors using a framework like STRIDE to systematically consider different types of threats. Finally, we will analyze the vulnerabilities and risk, assessing the likelihood and impact to prioritize our mitigation efforts. Threat modeling is an essential cybersecurity practice that helps us stay one step ahead of malicious actors. Secure design patterns and architecture. Secure design patterns are proven, reusable solutions to common security problems in software architecture and design. By applying these patterns, organizations can build systems that are inherently more resilient and resistant to attack. This reduces the surface area for vulnerabilities from the outset. The first pattern is the principle of least privilege. This means designing systems to that users, programs, and processes are granted only with the minimum necessary permissions to perform their intended functions. This reduces the potential impact of a compromise. The second pattern is the defense in depth strategy. This involves implementing multiple independent layers of security control throughout the system. This layered approach ensures that if one security mechanism fails, others are in place to continue protecting the system. The third pattern is secure defaults. This means ensuring all system components, applications, and configurations are set to the most secure state by default. This minimizes the risk of misconfiguration by users or administrators. The fourth pattern is fail secure. This means designing systems to fail to a secure state rather than an insecure one. In the event of system failure or error, access should be denied or capabilities limited to prevent unauthorized operations. So, move to the next slide, the secure development. This slide covers the secure development phase of the security lifecycle, which focuses on embedding security directly into the coding processes. The secure coding practices are essentially including input validation, error handling, and robust authentication to prevent common vulnerabilities like SQL injection and XSS. The static application security testing, SAST, tools can automatically analyze code for vulnerabilities without execution, identifying issues early and enabling proactive fixes. DAST, dynamic application security testing, tools simulate real-world attacks to find runtime vulnerabilities and configuration errors complementing SAST. Software composition analysis tool manage risk from open source components that third-party libraries by identifying dependencies and remediating vulnerabilities. The continuous security training for developers is crucial to foster security-aware culture and ensure they are the first line of defense. Secure coding practices. The secure coding practices are fundamental to building robust and resilient software. They involve adhering to guidelines and principles during development to minimize vulnerabilities. This helps reduce the attack surface and make applications more difficult to compromise. The key secure coding practices include input validation and sanitation to prevent injection attacks, secure authentication and authorization to control access, proper error handling and logging to avoid disclosing sensitive information, use of strong up-to-date cryptography for data protection, actively managing and updating third-party dependencies to address vulnerabilities. Next slide is secure automated testing stack. This slide introduces the concept of a secure automated testing stack, which integrates various security testing tools and methodologies into CI/CD pipelines. The key components of these stacks are static application security testing, analyzes code without execution to detect vulnerabilities early in the development process. Again, dynamic application security testing. This tests running application by simulating external attacks to uncover runtime vulnerabilities. IAST, interactive application security testing, combines SAST and AST, providing the real-time feedback on vulnerabilities and pinpointing the exact line of code. Software composition analysis. This automates the identification and management of open source components and third-party libraries, scanning for known vulnerabilities and tracking licenses compliance. Implementing this secure automated test stack ensures continuous identification and remediation of vulnerabilities. Automating detection and speeding up the feedback loop to embed security in the release process. So, stage 3, integrating DevSecOps. Integrating DevSecOps embedded security across the entire software development lifecycle from initial design to operations. This approach leverages automation, collaboration, and continuous feedback to make security an inherent shared responsibility. This leads to faster, more secure software release and a stronger overall security posture. Continuous security integration. Security is embedded within the CI/CD pipeline with automated checks, scannings, and policy enforcement. This shift-left approach identifies and remediates issues early, reducing cost and risks. Security automation and orchestration. Automate security tasks like code analysis and compliance checks. This reduces human error, accelerate feedback, and free security teams for strategic initiatives. Culture of shared responsibilities. Foster a collaborative environment where security is collective responsibility. Promote cross-functional training and communication to build security into product from the ground up. And policy as a code. Define security policies as version controlled, executable code. This ensures consistent automatic enforcement across the CI/CD pipelines and infrastructure, integrating compliance directly into the development. Continuous monitoring and feedback loops. Implement continuous monitoring in production to detect anomalies and threats. Robust feedback loops feed operational insights back into development, ensuring interactive security improvements. The secure automation is essential for efficient DevSecOps pipelines, seamlessly integrating security processes with minimal manual intervention. Automating routine tasks reduce human error, accelerate vulnerabilities remediation, and empower security teams to focus on strategic initiatives. Automated security policy and configuration enforcement ensures compliance with the baselines, access controls, and data protection standards to prevent misconfigurations. Automated workflow quickly identify, prioritize, and initiate remediation for vulnerabilities, drastically reducing the window of exposure. SOAR platforms automate incident response, threat intelligence and security operations, minimizing impact and enhancing team efficiency. Automating configuration and monitoring of security settings in cloud environments ensure adherence to best practices and compliance requirements. Secure governance as code. Integrate security and compliance policies directly into the DevOps pipeline by defining them as executable code. This approach leverages version control and automation, transforming manual governance into an automated, scalable systems for enhanced security and regulatory compliance. Automated policy enforcement. Security policies and compliance rules are defined as code, allowing automated tools to continuously check and enforce adherence across all environments, preventing misconfiguration and ensuring a consistent security baseline. Version control and auditability. The policies are stored in a centralized version control repositories, providing a clear audit trail of all changes. This simplifies compliance audit and enables easy rollbacks, fostering transparency and accountability. Integration with infrastructure as code. Governance as code integrates with infrastructure as code tools. Policies are automatically applied during infrastructure provisioning, ensuring new environments are secure by design and comply with the regulations, reducing the attack surface. Move to stage 4, secure operations. Secure operations is the fourth stage in the cybersecurity lifecycle, focused on maintaining system and application security post-deployment. This stage ensures continuous protection, swift incident response, and ongoing optimization of security control in live environments to safeguard data and system availability. Key elements include continuous security monitoring and threat detection using SIEM and EDR tools to identify suspicious activities and potential threats in real time. Establishing a comprehensive incident response plan with clear procedures for identification, containment, eradication, recovery, and post-incident analysis to minimize damage and learn from events. Collecting and centralizing security logs for comprehensive audit and forensic analysis. Providing crucial evidence for incident investigation, compliance, and identifying attacks patterns. Enforcing strict access control and privilege access management (PAM) to limit user permissions and reduce unauthorized access risks. Regularly reviewing and revoking unnecessary rights. Secure monitoring. Secure monitoring is crucial for robust security, providing real-time visibility and a prompt detection of anomalies. By continuously analyzing logs, network traffic, and system activities, organizations can identify suspicious patterns, respond swiftly to incident, and proactively mitigate risks. Implement continuous monitoring and advanced analytics and AI to detect suspicious activities and malware across endpoints, networks, and applications. Centralize and aggregate the security logs into SIEM systems for comprehensive event correlation, streamlined analysis, and efficient incident investigation. Utilize UBAR tools to establish baseline behavior and automatically identify deviation, detecting compromised accounts, inside threats, or sophisticated attacks. Monitor network traffic for malicious activity and policy violations. Deploy IDPS to alert or block suspicious patterns, protecting against common and advanced network-based attacks. Next stage is secure adaptive defense. Secure adaptive defense is a proactive, dynamic approach to cybersecurity that continuously evolve proactive measures to address emerging threats and changing attack vectors. It goes beyond static perimeter-based defenses by leveraging real-time threat intelligence and advanced analytics to predict, detect, and automatically respond to the sophisticated attacks. This strategy ensures resilience enterprise systems by maintaining a posture that adapts to the evolving threat landscape. The AI-powered threat prediction utilizes machine learning to analyze threat data and anticipate adversary tactics, enabling primitive defense. Dynamic policy enforcement automatically adapts security policies based on detected anomalies, keeping defenses aligned with the current risk profile. Automated remediation and self-healing systems rapidly respond to vulnerabilities or breaches, minimizing impact and restoring system integrity. Continuous feedback loops integrate incident response, threat intelligence and vulnerability data to iteratively improve the defense system's resilience. Use case, automotive. So the global automotive IoT platform we have built integrates connected vehicle telemetry, over-the-air updates and customer mobile apps. To secure this platform, we took a multi-pronged approach. Conduct thorough threat modeling to identify over 40 high-risk scenarios in the design. Embedded security guardrails into our infrastructure as code and API templates through policy as code. Automated SaaS, DAST and container scanning in our CI/CD pipelines. Integrated our security orchestration and automated response solution to triage and response to runtime alerts. The outcome have been very positive. The 80% reduction in our vulnerability backlog within 6 months, 60% decrease in mean time to remediate, and 50% reduction in audit preparation time due to continuous compliance. Smart factory. This slide outlines our approach to security smart factory environment, which involves advanced malfunction manufacturing with robotics, IoT and AI-driven predictive maintenance. Key elements of our approach includes converging OT and IT security policies for a unified security posture, hardening IoT devices with secure configuration, updates and identity management, protecting the integrity of AI models and data used for predictive maintenance, implementing network micro segmentation to isolate critical production zones, automating vulnerability management through continuous scanning and patching. The outcome we aim to achieve includes 75% reduction in unplanned production downtime, 99% integrity of production data, 50% reduction in mean time to contain OT security incidents, 40% improvement in compliance with security standards. This next cloud data estate, this is one of the use cases. This slide outlines the use case for cloud data estates, a multi-cloud data platform for sensitive customer data and AI model training. The key approaches taken includes the threat modeling to identify high-risk scenarios and integrate security controls, embedding security and data masking rules into infrastructure as a code templates using policy as code, automating SAST and DAST and container security checks in the CI/CD pipelines, integrating SOAR to link alert to automate access revocation, reducing response times. The outcomes achieved includes 85% reduction in critical high priority and vulnerabilities in the backlog, 55% drop in mean time to remediate security incidents, 60% decrease in time required for regulatory audit preparations. So how we measure the success? The effective security measures requires a comprehensive approach to measure success. We track a variety of metrics to assess the speed, stability and security of our software delivery process. DORA, the metrics like deployment frequency, lead time for change, MTTR and change failure rate help us evaluate the efficiency of secure software delivery. Vulnerability management metrics like reduction in vulnerability backlogs, time to remediate critical vulnerabilities and patch complaints rate demonstrated the effectiveness of our proactive security measures. Compliance and audit metrics help us ensure adherence to industry standards and regulations, as well as the efficiency of our audit preparation process. Incident response and automation metrics such as MTTC and MTTR and percentage of automated security responses highlight our adaptive defense capabilities. Call for action and close. Start small with the pilot project to demonstrate the value of a security first approach and learn what works best for your organization. Apply security consideration at every stage of the software development lifecycle from design to operations. Scale security practices across the enterprise by automating security tasks and cultivating a security-minded culture among your teams. So this is what like we recently started in my organization. So it's like we had taken a POC as one small project from the beginning. Like we have taken legacy application and we are migrating into applying all these standards and security stuff. So we are seeing a good results out of it by following these principles and all. Yep, that's it. Thank you. Any questions?
I have a question. When you went through your use cases, you had designated some key techniques for each one of them. Were you able to tie those? How did you identify that those were the key techniques, or were those simply the techniques that were used in those use cases, or were you able to identify that those were the particular things that resulted in the decreased time frames, for example, for closing issues?
Yeah. So by using these principles and all, like we use it on all the use cases. For example, like I'm working for a manufacturing company where we have IoT and all. So we identified all these and we started applying these principles, and we are able to have some logs. We're maintaining the metrics. So with that metrics, we're able to see these are the data, whatever I given. It's not accurate, but it's near to that data.
Yeah. All right. Thank you.